All right, so I have a data set here that is 1,000 dice in a bucket, and I have the colors and the weights of each dice in that bucket. We're going to treat this like a population, and we want to find, say, the population mean weight. So if you've got the population, you can just in StatCrunch do summary stats on the columns. Going to pick the weights and calculate the mean. So we get that the population mean weight is 4.6 grams, so 4.64485. Now, usually you don't have a population, and taking a census of a population is too time consuming, takes too many resources, right? So we have to come up with a way to figure out what this population mean is by taking a sample. So let's take a sample. So I'm going to go to data sample. I'm going to choose weight, and let's take a sample of, say, 30 of the DOS. So StatCrunch randomly chose 30 of the weights, and we could find the sample mean of these weights. Same thing, we can go to stat, summary stats columns, and find the sample weight mean. And we see that we get a sample mean that is 4.4556667. Now, this is not the same as our population mean, but this is, it's as good as we can do with this one sample. If we had more time and more resources, let's say that I wanted to continue this experiment, I could redo this sampling over and over. So let's say we did this same experiment. Going to take samples of size 30, but let's do 100 samples. So I just keep dipping the cup into the bucket, weighing all the dice, and then repeating the process. And we did it 100 times. You see we've got 100 new columns of weights. And I could find the sample mean of each sample, and they would all be different, right? We'd all get different sample means because all these samples are different. They were just randomly chosen from my population. So we could combine all of these sample means together. So let's go to stat, summary stats columns. And I'll include the first sample I did as well. I'm going to scroll down to the bottom. I'm going to hold down Shift. So I select all of my samples, and I'm going to choose mean. And I'm going to store this in the data table. That way I'll get a column with all the means in it. All right, so at the end of my data set, I have a column with all the sample means of all of those samples. And remember, I'm trying to figure out what the population mean is with these sample means. So one thing I could do is find the mean of all the sample means. And here, we're using the central limit theorem, right? So the mean of my sample means is 4.6438746, which is closer to the population mean than I got with just one sample, right? But it's still not exactly the same, but I got closer. So another way to think about estimating the population mean would be, instead of just picking one value, let's pick a range of values. So, let's find the middle 95% of these sample means and see what range I have of my sample means. So I'm going to go to Stat, Summary Stats Columns. I'm going to pick the column that has all of those sample means in it. And then at the bottom here, I'm going to choose percentiles. So if I want the middle 95% of a data set, there's minimum and maximum of my data set, and I want the middle 95%. Well, that means there's 5% on the outside, which means there's 2.5% on the left side, and there's 2.5% on the right side. In terms of percentiles, if I want to know which values separate out the middle 95% from the rest, this would be the 2.5th percentile, because it has 2.5% of the data to the left. And if I want to figure out this one, it's going to be 95% plus the 2.5%. That's going to be the 97.5th percentile. So if I want to figure out the middle 95% of my data set, I'm going to find the 2.5 percentile and the 97.5 percentile. So let's go back to my summary stats calculator, and I'm going to, in the percentile row, I'm going to type in 2.5 and 97.5. That's going to give me a range. So now I can say, well, my sample mean was 4.64, but I'm going to give myself some leeway here. I'm going to say, 95% of the sample means that I calculated when I took 101 samples of size 30, 95% of those were between 4.46 and 4.81. So we have a confidence interval I know 4.81 was the one on the right. What was the one on the left? 4.46. So 95% of my sample means in my data set were between 4.46 and 4.81. So I could say I'm 95% confident that that's where the population mean is. All right. Now, you might be saying, well, I don't want to have to take 100 samples of size 30. So with bootstrapping, we're going to simulate this same process of resampling, but we're only going to use one sample to do it. All right, so let me get rid of these columns and move these over. So we're going to start over, and this time we're only going to take one sample. So just going to take a new sample of the weights. Let's do 30 again. So I've got a sample of size 30 of the weights, and StatCrunch randomly chose them from the weight column. So in bootstrapping, the reason why we call it bootstrapping is that the sample is going to pull itself up by the bootstrap and become the population. So we're going to assume that this sample is representative of the population, and we're going to resample this one sample with replacement, meaning we're going to take samples of size 30 from this sample of size 30, but we're going to use with replacement, which is going to allow each data value to be chosen multiple times. So it gives you more options there. It gives you more possibilities for the samples. So in StatCrunch, it's really easy to take a bootstrap resampling. You're going to go to Applets, Resampling, you're going to bootstrap a statistic. And I'm going to choose the sample, right? We're pretending we don't actually have the population. So we're going to choose the sample that we took. We're going to bootstrap the mean, but you can also do other statistics there. And we're going to click compute, and we get a new applet here. So what this is going to do is resample my sample multiple times. And it's going to calculate the sample mean of each sample, and it's going to list those samples in a histogram. It's going to make a frequency histogram here of the sample means. So I'm going to do this 1,000 times, and I like to just keep doing this until I get to 10,000. You see we get a nice close to normal distribution shape. And these represent all the sample means. And here the mean of my distribution is 4.71. And it also gives me these automatic percentiles. So it gives me the 2.5 percentile and the 97.5th percentile. So I get 4.48 to 4.95. So 4.48 to 4.95. So that is my bootstrapped confidence interval. And we'll say we're 95% sure that our population mean weight is between 4.48 and 4.95. And it actually is, right? Our population mean was 4.64. The mean of this bootstrapped distribution was 4.71. That's given up here as well. So that's our point estimate. We would say this is our single value estimate. If I could only pick one value to estimate what the population mean is, it would be 4.71. But the confidence interval gives us a range. It gives us a margin of error, right? So we can say we're 95% sure it's between 4.48 and 4.95. Now, if we wanted to use a different percentage, let's say we wanted to use 90%. So what would the middle 90% be? Well, that would mean that there would be 5% outside of that, right, on each side. So 10% total, 5% on each side. That would mean I would need to find the 5th percentile and the 95th. Okay, so our applet for bootstrapping automatically gives us the 5th percentile, 4.52, and the 95th percentile, 4.91. So 4.52 to 4.91. That would be our 90% confidence interval. And notice that this interval is smaller. The limits moved in closer together, but we're only 90% confident in it. And that makes sense. The 95% confidence interval that we made here, it casts a wider net to try to capture what that population mean is. So the wider the net, the more confident you can be that you've actually captured it. And this one has a smaller net, right? But sometimes you want a narrower estimate, but you can't be as confident in that result. Another way to get these closer together is to take a bigger sample. So if we take a sample of size 100, for example, let's do that. We take a sample size of 100, our confidence interval should be better. So sample, I'm going to sample the weights. Let's do 100 this time. I'm going to use the resampling bootstrap a statistic. option in StatCrunch. I'm going to pick my second sample, and I'm going to do this 10,000 times again. Now you see that I'm going from 4.55 to 4.78 in the 95 percentile, or sorry, 95% confidence interval. And those are closer together than the ones I had before. So you get a better estimate if you take a bigger sample, and you see that the mean here, the mean of all my sample means there is closer to the actual population mean as well. Okay, so how do you do this for proportion? Let's say that we want to take a sample of size 100 of the colors. Instead of the weights, let's do colors. So now I've got a column of just the colors of the DOS. And let's do a frequency table on those colors on the sample. And in my sample, let's say I got 13 red DOS out of 100. So it's 13% or a proportion of 0.13. And I want to create a confidence interval for the proportion of red DOS in my population. And I'm going to use that confidence interval to estimate what the population proportion is. So I want to know what percentage or what proportion of the DOS in my bucket are red. Okay, so I got 13 out of 100. When you use the Bootstrap applet in StatCrunch, for proportions, you're actually just going to use a summary. So you're just going to tell it how many times you had a success, and how many times you ran the experiment, or how many, what's your sample size, right? So I got 13 red out of 100. I'm going to resample 10,000 times, and I get a confidence interval, a 95% confidence interval that's from 0.07 to 0.2. So we're going to say, we got a confidence interval, or we got a sample proportion that was 0.13, 13%. Our confidence interval says we're 95% sure that the population proportion is between 7% and 20%. Now let's check and see how good that estimate is. Let's find the population proportion of red DOS. So I'm just going to take, I'm just going to make a frequency table for the population of colors. And I see that there's actually 20% of my population is red, and that was included in my confidence interval. So the confidence interval did a good job of capturing that population proportion, but it was on the edge, right? So if we'd have made a 90% confidence interval, then it wouldn't have worked. So that's another thing, you're going to have error, because if you're only 95% confident, 5% of the time, your confidence interval is not going to contain the population proportion just by random chance in the sampling. And if you're 90% confident, then you're saying that there's a 10% chance that your confidence interval does not contain the population mean or population proportion. All right, so that is bootstrapping a statistic to get a confidence interval.